Okay, I want to talk for a few minutes about conservation of energy, how it because this is kind of the overall uh, law of nature that ties in work and energy with each other. And so you can't talk about work and you can't talk about energy without addressing the conservation of energy. We have a lot of problems regarding conservation of energy, so it's a pretty important concept. First, I want to talk about mechanical energy. Now, real simply, mechanical energy is something that's produced by a machine. Now, don't forget, people are considered machines. So, we can produce mechanical energy when you throw something or when you apply a force to something. Basically, it's kind of hard to define mechanical energy. The best definition I've been able to find is that it's a form of energy that's associated with motion or a force, a physical force. Now here's some of the more common types of mechanical energy. Kinetic potential energy. I'm specifically referring to gravitational potential energy here. And then elastic energy, which is energy stored up in a spring. The two that we're going to focus on are kinetic energy and the potential energy, the gravitational potential energy. A lot of times, the stuff with mechanical energy can include elastic potential energy. I'm just not going to include it. If there are no dissipative forces present, and primarily what we're talking about is friction. So in the absence of friction, mechanical energy is conserved. Now, I kind of want to go over the conservation law again, and I'm going to present it incredibly generally and simply refer to it as the law of conservation of whatever. And you can fill in the blank of whatever is: mass, energy, charge, momentum, angular momentum. I mean, it's the same wording. Whatever cannot be created or destroyed, but it can be transferred. And what that means is the total amount of whatever we're dealing with that you begin with is equal to the total amount of whatever you end with. Now, here's the thing. The total amounts are the same. The individual components can change, and they typically do change. But the overall amount does not, like in the conservation of momentum. The individual momentums of the objects will change when they interact, but the total momentum does not. And that's the whole idea with the conservation of whatever. And so I'm going to put in for the whatever mechanical energy, the conservation of mechanical energy. Our initial mechanical energy is equal to the final mechanical energy. And that's in the absence of absence of friction, sorry. Now, the mechanical energy is simply all the kinetic and all the potential energy. Gravitational, elastic potential energy. The initial kinetic and the initial gravitational potential and the final. This is nice, but like it just says, it only applies when friction is negligible. An example, a pendulum, that if you allow to swing back and forth just a few times, friction can be considered negligible. But almost more than 3, 4, 5 times, friction is playing a big role. And so you can't do conservation of mechanical energy. It's nice, but I prefer a more global approach. I like to look at things simply as conservation of energy. So let's take an example, and let me kind of discuss what I'm talking about a little bit. Consider a child going down a slide, and we're going to look at this first situation when there is no friction. He climbs up to the top of the slide. He has a bunch of potential energy, gravitational potential energy. It gets converted to kinetic energy. That's it. At the bottom of the slide, all that potential energy that he began with got converted to kinetic. There's conservation of mechanical energy. Now, a more realistic consideration is there is friction. And so what happens? You still begin with the gravitational potential energy. Some of that potential energy gets transferred to kinetic energy. So you start picking up speed as you go down the slide. But some of that potential energy is then used to overcome the friction, and it appears as heat. Now, some might say the potential energy gets converted to kinetic energy. That kinetic energy gets converted to friction, to heat. I'm not going to me, that's a detail. Basically, you're starting with a bunch of potential. Some of it goes into kinetic energy, some of it goes into friction. So, how I like to look at conservation of energy. Your total initial energy is equal to your total final energy. In other words, in just the things that we're going to look at, initial kinetic and initial potential is equal to final kinetic and final potential plus friction. We're going to begin with a bunch of kinetic and potential energy. All of this initial energy is going to get converted to other amounts of kinetic and potential energy. Some of that initial energy might also go into friction and to overcome friction. So I like to look at not the conservation of mechanical energy, but the conservation of kinetic energy. I like to look at this type of expression more than anything else, because then if we do have friction in the expression, it's accounted for. If we don't have friction in the problem, then this term is zero, and it still applies. So that's how I like to approach any problems that we'll be doing in class, with this type of an expression. Now, kind of reiterating what I'd already talked about. One type of energy gets converted into some other type. If an object is falling, the potential energy of the object gets converted into kinetic energy. If there's air resistance, some of that initial potential energy might get converted into friction also. That's where that friction is an overencompassing term that accounts for all forms of resistance. If we're talking about a ball that's rolling up a hill where we have initial kinetic energy, as it goes up the hill, the kinetic energy decreases, potential energy increases. It's really just kind of that simple. And again, some of the initial potential or kinetic energy may also be used to overcome friction. Now, going back to my analogy that energy is money, work is spending the money, or work is like your job in which you earn money. Either way is fine. Then how this is kind of viewed as what we begin with. This initial energy is how much money do you have? That's what we're talking about. It could be in the form of kinetic energy, potential. What that goes to is some final amount. You can have, and you might be buying stuff. And so this is the stuff that you buy. Your final kinetic, your final energy is the stuff that you buy. This friction would be the taxes that you pay. And so you're going to start off with like maybe $100. You start off with $100. From that, you might only be able to buy $90 worth of goods, because you know there's going to be a tax. And so some of that initial $100 is going to go into the tax. And so in this case, it might be $10. And so that's kind of how I'd like to view energy and work and something a little bit more concrete, because energy is a vague term a little bit, and I need something a little bit more concrete to get my hands around. Okay, just a quick practice problem. I'm not going to go through all the details in the practice problem, but I suggest that you do. And it's a pretty simple example. Let's take a 1 kilogram book, and let's drop it from a height of 2 meters, and we're going to assume no air resistance, okay? Now, what you should be able to do is to figure out how much kinetic and potential energy is present at the instant the book is released from the 2 meter height. Then, also figure out the potential and kinetic energy when the book has fallen 1.5 meters or it's half a meter above the floor. And then the potential and the kinetic energy just as the book reaches the floor. Now there's a bunch of ways you can do this. I would start with finding this initial potential energy just before it's released. It's based on a height of 2 meters. The instant the book is released, the kinetic energy is 0. So that term goes away. So the total amount of energy that we have is the amount of potential energy at 2 meters. That number does not change. Conservation of energy. Down here, we can find the potential energy when the book is half a meter above the floor. That's pretty easy. What I know is this potential and this kinetic energy has to add up to my original potential energy. So I just subtract it. I subtract this potential energy from my original potential energy, and I can get my kinetic energy at 0.5 meters. I can also do the kinematic equations, figure out based on free fall calculations how fast the object is going after it has fallen 1.5 meters, and then plug that into my kinetic energy equation, and I'm going to get the exact same number. The last part, the potential energy and the kinetic energy just as the book reaches the floor, well, basically when it's at the floor it has no height, so the potential energy is 0. Which means the kinetic energy has to be from all the initial potential energy. And so that's one way of viewing this problem. So here's the table that I came up with, and I'm not going to go through all the details, but you can see it. And I'm just going to explain. This is the height that the object is at. This is how much potential energy it has at that height. This is how much kinetic energy. And this is the total amount of energy it has. I have it labeled as mechanical energy. It's the total amount of energy. This number does not change. The total amount of energy does not change. Conservation of energy. But as potential energy decreases, kinetic energy increases. Okay, that's a quick, short, simple, sweet and simple view of conservation of energy. The problems we do in class will reinforce these ideas.